Our goal in 3.4 is to use derivatives to maximize or minimize or optimize, if we want to summarize that together, a particular value given certain parameters. So optimization means to find possible parameters that will either create a maximum or minimum output for a given situation. In order to do this, we need to know an explicit equation that relates the variables. We need a secondary equation that will allow substitution in case we have too many variables on one side. We need to always be thinking about the domain of a particular problem. We're not going to talk about negative side lengths of a box or different things like that. You just need to make sure you're paying attention to the domain in the context of what we're talking about. And then we need to know criteria for finding the max or the min, which is going to involve first derivatives, critical values, number lines, second derivative tests, all the tools that we have been using and building up to this point. So when we're working through problems like this, always make sure, just like with related rate problems, that you're drawing a picture and choosing your variables. Make sure you're identifying the primary equation. If we're trying to maximize volume, the volume is going to be the primary equation. If we're trying to maximize surface area is going to be the equation that we're using. So make sure you write a primary equation and you isolate whatever is going to be maximized or minimized. Then you're going to rewrite with only one variable on each side, which may mean that you need to use a second equation and use that to substitute back into the original primary equation. Again, make sure you're paying attention to the domain. Take the derivative and analyze the critical numbers, make a number line so that you can determine whatever value you're being asked about. So that's really the process that we're going to go through today. We're going to do 3 or 4 examples and really kind of hit into what this looks like. Okay, for this first example, we have 48 square centimeters of cardboard, and we're going to make a box that has no top. The box must have a square base, which you can see in the picture. Both of the base lengths are W. What dimensions would give us a maximum volume? So this problem doesn't seem like it has a lot of information, but let's dissect what's here. Our ultimate goal is to maximize the volume, which means right away I want to be thinking about what is the volume here. Well, the volume is going to be the base, the area of the base times the height. What else do I know? I know that I have 48 square centimeters of cardboard. That's giving me the surface area. So we're given that the surface area is 48 centimeters squared. And then we can actually identify the surface area is just going to be the area of the base plus the area of all the sides. So we can set up a new equation. The surface area, 48, is going to equal the area of the base is W squared, and then the area of the 4 sides going around, remember there's no lid or no top to this box, is going to be W times H, and since there's 4 of them, that's going to be 4 times W times H. Now we want to be able to have one equation with volume on the left and everything else in terms of one variable, so I'm going to go ahead and take this surface area equation and I'm going to solve for H so that I can substitute that into my volume equation. So if I solve for H, I'm going to get H equals 48 minus W squared over 4W, and I'm going to substitute this expression in for H in my volume formula. Then I'm going to go ahead and simplify this. So I'm going to get volume equals 12W minus 1/4 W cubed. So I've accomplished my first 2 steps. I have a picture, I've chosen variables, I wrote my primary equation. I used another equation so that I could put my primary equation in terms of only one variable. And now we're going to differentiate with respect to that one variable. So we're going to differentiate our volume with respect to W. That's going to give us dV dW equals 12 minus 3/4 W squared. Now I'm going to take that and I'm going to find my critical values. So subtract 12, multiply by 4/3. So I'm going to isolate W squared. That would actually give me that W squared equals 16, which means that W is going to equal 4. Notice I'm not including -4. It doesn't make sense for me to have -4 as a length of my box. Now I'm going to make my number line, and when I make my number line is when I'm really going to think about domain restrictions. So this really needs to end at 0 because I can't have a negative side length. The only critical value that we just found was 4. And the maximum that that W could possibly be, and it actually couldn't be this value, so this would be an open circle, but is the square root of 48. If 48 is how much cardboard I have, then if all of the cardboard was used for the base, which I know doesn't really make sense because then it would be two-dimensional, but that's the point of finding an upper limit. The most it could possibly be is the square root of that area to get that one side length. So W has to be somewhere between 0 and 48. It really can't be equal to 0 or equal to 48 because that wouldn't make sense for the type of object that we're talking about. Now I can fill in this sign chart. If I plug in something like 1 into our dVdW, I'm going to get a positive number. If I plug in something like 5, I'm going to get a negative value. So there's my sign chart. That means I'm moving from increasing to decreasing, so I'm going to have a relative max when W is equal to 4. And that's going to be true since dVdW is moving from positive to negative at that value. The question asked us for the dimensions of the box, so the box would have a width of 4 and a height of 2. So the dimensions would be 4 centimeters by 4 centimeters by 2 centimeters. And I just found out that h was 2 by plugging 4 into the equation over here that we came up with for solving for h. So again, starting with that process, draw a picture if there's not one given, identify your variables, figure out your goal. That's going to help you determine your primary equation and isolate what needs to be maximized or minimized. If there are any other formulas that are going to come into play, make sure you bring those in and use that to substitute back into the primary equation. Find the critical values by taking the derivative. On your number line, make sure you're considering the domain restrictions that exist. And then from that number line, determine your maximum or minimum, whichever you're talking about in the context of the problem. So let's work through a couple more examples. Okay, number 1 says the sum of two numbers is 30. Find both numbers if the sum of twice the first plus the square of the second number is maximized or minimized. So something that I meant to add in these directions, please make sure we're only considering positive values. This would be a very different problem if we were considering both. So let's identify what we have. First, I'm going to define my variables. I'm going to let x be my first number and y be my second number. And I'm going to let a be that value that we are maximizing and minimizing. So there's not really a picture to draw here. I'm going to go ahead and set up the equations based on the information that they're giving us. So I know that x plus y equals 30. And I also know that 2x plus y squared equals a, which is what I'm trying to maximize. I'm going to go ahead and take this first equation and I'm going to solve for y. This is going to be y equals 30 minus x. And I'm going to substitute that in to the second equation. So that's going to give me 2x plus, if I just do a little algebra and square 30 minus x squared, that's going to give me x squared minus 60x plus 900 equals a, and then I'm going to combine like terms, x squared minus 58x plus 900. So I defined my variables, I used the two equations to combine them to be one equation involving isolated a, so the thing I want to maximize by itself or minimize. Now I'm going to go ahead and take the derivative with respect to the variable on the right, so with respect to x. So dA dx is going to be 2x minus 58, which means that my only critical value is going to be when x is 29. Now we're going to go ahead and think through the values that x can be. Since x has to be positive, the lowest it could ever be is 0, the highest it could ever be is 30, and the only critical value that we found is 29. So this is my dA dx number line here. If I plug in something like 1, I'm going to get a negative number. If I plug in something between 29 and 30, I'm going to get a positive number. So now I need to analyze the cases. I'm actually going to draw a line, and I'll talk through B in just a minute, but I'm going to analyze the cases. There are 3 possible values for x. X could either be 0, 29, or 30. So I need to figure out what the y values are, or what the y values and the a values are, to figure out which is the max and which is the min. If x is 0, that would mean that y is 30, since their sum is 30, which would mean that a is 30 squared, which is 900. If x was 29, then y would be 1, which means that a would be 2 times 29 plus 1 squared, so that's going to be 59. And if x is 30, that means that y is 0, which means that a is going to be 2 times x, which is 60. So now, using this information, I can identify where the max and min values would be in context to this problem. So the maximum is 900. The maximum value is 900, and that happens when the first number is 0 and the second is 30. And then for part B, which I'm going to just try and squeeze right here, the minimum is 59, and that occurs when the first number is 29 and the second number is 1. So let's go ahead and look at a couple more examples. All right, number 2. A rectangle is bound by the positive x and y axes and the line y equals -1/2 x plus 3. And we are going to maximize its area. So what should the length and the width of this rectangle be? So let's go ahead and first draw a picture of what this is talking about, and note that we want to maximize the area of the rectangle. So I've set up my picture by just drawing the line y equals -1/2 x plus 3, binding this with the axes, and just sketching out what I'm talking about. I'm talking about this rectangle here. The formula for the area of this rectangle is going to be area equals x times y, but we also know that y is equal to -1/2 x plus 3, so we can go ahead and substitute that in. Now I have the variable that I want to maximize isolated on the left, and the right hand side is only one in terms of one variable, so I can differentiate with respect to that one variable. So dA dx is going to be equal to -x plus 3, which means my only critical value is going to occur when x is equal to 3. I'm going to go ahead and make my number line. Thinking about domain restrictions, this is bound by the x-axis on one side. It's bound by the line y equals 1/2 x plus 3, which touches the x-axis at 6. So it's bound by 0 from the y-axis. I think I said the x-axis before. It's bounded by from 0 on the y-axis and 6 where the line crosses. And then we just found our critical value to be 3. So I can test what's happening in between. Between 0 and 3 in my derivative equation, I'm going to have a positive value. Between 3 and 6, I'm going to have a negative value. So we can say that the area is maximized when x equals 3. If you had to justify, you would say since dA dt changes from positive to negative there. So the dimensions would be 3, and then if I plug 3 into y equals -1/2 times 3 plus 3, I would have 3 by 3 over 2 would be the dimensions of this rectangle. All right, let's work through one more problem. The last question says, and it has two parts, which point on the graph y equals the square root of x is closest to the point 5, 0? What about 0, 5? And this little symbol means I'm going to have you use a calculator for that part there. So I'm going to go ahead, draw the graph of y equals the square root of x, and plot the point that I'm talking about for part, I'm going to call this part A, where we're looking at closest to 5, 0. So we're talking about the distance from a point to this function. So the distance formula, thinking back, it's like the square root of the Pythagorean theorem, right? So the distance is going to be equal to the square root of x minus the x value, which in this point we're talking about is 5, x minus 5 squared, plus y minus the y value squared. Except something to note is that I need to only have one variable on the right-hand side, so I actually need to use the fact that y equals the square root of x. So that's going to give me that the distance equals, and I'm going to go ahead and multiply this out, x squared minus 10x plus 25, plus if I square the square root of x, I'm just going to get x. So really d is going to equal the square root of, actually I'm going to write it as rational exponents, x squared minus 9x plus 25 to the power of 1/2. I want to write it that way because the very next thing I'm going to do is take the derivative with respect to x. So dd dx is going to equal 1/2 times x squared minus 9x plus 25 to the power of negative 1/2 times 2x minus 9 if I take the derivative of the inside. And this is really just going to be 2x minus 9 over 2 times the square root of x squared minus 9x plus 25. The denominator is never going to be equal to 0, so in terms of critical numbers, the derivative is defined everywhere. So where is it 0? It's only going to be 0 when x is 9 over 2. It's less important for me to draw a number line here because I just found the x value that's going to get me closest to the value I'm talking about. There's only one value to consider. So I'm going to go ahead and substitute that in to my original function. That's going to give me 9 over 2 and the square root of 9 over 2, which is the same thing as 9 over 2, comma, root 3, oops, not root 3, 3 over root 2. You do not have to simplify there. So this would be the solution for part A. I'm going to do part B on the next slide. So now we're looking at the same curve, y equals the square root of x, and we're identifying what point on that curve is closest to the point 0, 5. So again, we're going to be looking at the distance. So since I'm using the letter D again, I'm going to use a subscript like the number 2 to talk about this distance. I'm going to plug in the point 0, 5. And then remember, I need to get rid of this y, so I'm going to substitute in that y equals the square root of x. So when I substitute in the square root of x and then I multiply out square root x minus 5 quantity squared, I'm going to end up with this. And then I can combine like terms or simplify or simply leave it just like this since we're allowed to use a calculator here. That's what this little asterisk means you're allowed to use a calculator. So if we use our calculator to identify our critical values, which you could just graph, set this in your calculator as y1, have y2 in your calculator be d dx of y1 when x equals x. Set it to graph and then hit second calc or second trace to find the zeros. So let me know if you need help with the calculator portion of that. I'd be happy to work with you. So using a calculator then, we can find our critical numbers with a calculator. And I'm just going to tell you that we get that x equals 1.525 as our critical value. So that means the closest point on the curve, y equals the square root of x, to the point 0, 5 is 1.525. And then if I plug that into the function, I'm going to get 1.235 as my y value. So that's going to give you the closest point. So to recap these notes, make sure you draw a picture as necessary. You identify the primary equation and isolate whatever is being maximized or minimized. That you use any substitution for a secondary equation to make sure that you just have the thing you're being maximizing or minimizing equal to something in terms of one other variable. You're going to differentiate and make sure that you're keeping in mind the domain of what you're talking about for the context of the problem. Then you're going to find your critical numbers and evaluate where you have maxes and mins. Looking forward to working with you on this in class. Thanks.